the second part of protein is gelation. So what is protein gelation? Now, protein contributes significantly to the physical properties of food, and that includes its ability to build or to stabilize gel, foam, emulsion, okay, and many more. So this gelation actually refers to transformation of protein from the solid state to a gel-like state. And how are these protein gels are prepared? So you need heating, okay, you need heating, and then moderately concentrated protein solution, so means presence of water. So you need water, you need heating, okay, and that will form gel. So the protein is in a solid state, okay, when you prepare that moderately concentrated solution, okay. So when you apply heat, okay, it begins to denaturate, okay. So denaturation will happen, means the breaking of the structure of the protein, okay, due to the heat, okay, when water is being trapped within the nature state of the protein to form progel, okay, progel state. And when this condition cools down, okay, it will form gel, okay. Very simple example, if you have seen the local Sarawakian food, ambuyat, okay, they use sago, okay, then they use water, they heat it up to form very sticky kind of food, and they eat with sambal belacan, okay. So this is one example, okay. When it cools down, it form gel. So there are two types of gel that protein can form, okay. It's either coagulant or translucent. Another name for coagulant is opaque, okay. Opaque gel is due to hydrophobic interaction, okay. Translucent gel, on the other hand, is due to hydrogen bonding. So from here you can see one gel is from hydrophobic interaction, one gel is from hydrophilic interaction, okay. Now how these two different gel form? Now let us look at opaque gel first, or coagulant gel. So protein in its native state, okay, with large amount of non-polar amino acid residue, okay, will undergo hydrophobic aggregation, okay, when it undergo denaturation, okay. Remember, protein are made of amino acids, and opaque gel will form if the protein containing abundant of amino acids that belongs to the non-polar group, okay. And then these hydrophobic amino acids will aggregate, okay, when it denatured, okay. Denatured means when heat is applied, water is added at the same time, okay. And then this insoluble aggregation of amino acid, okay, will form opaque gel. So the rate of the aggregation will be faster than the rate of denaturation, means it aggregate faster than the rate of denaturation itself, okay. And it can even form gel while being heated due to the faster aggregation compared to the denaturation, Okay. However, this kind of gel, opaque gel or coagulant gel, is weak and easily prone to syneresis. So what does syneresis mean? Syneresis means the oozing out of water from the gel network. So remember when the gel undergo when it's become heated, undergo denaturation, okay, it traps water within the nature, okay, the native structure of the protein, okay. But then when it cools down, okay, and let it sit for days, month, it can undergo syneresis, means the network, okay, the gel network become disturbed. So when become disturbed, the water can ooze out. So means the gel now becomes smaller. Okay, very simple concept. You imagine you have towel, okay, different brand, okay. So one brand claim they have very superior absorb property compared to another one. So it can absorb water if without dripping out of if dripping off water. Okay, while the low quality towel, it cannot absorb water as good as the high quality, and water can drip out of the towel. So it's something like that. Okay, so when the water can drip out of the towel, it's actually undergo syneresis. Okay, it cannot contain the water that's being absorbed. So on the other hand, if the protein contain small amount of non-polar amino acid, means more of the polar amino acid, okay, it will be soluble. Okay, so it will form soluble complex, okay, when it undergo denaturation. Okay, so this soluble complex, okay, associate means they associate with one another is slow than the rate of the denaturation process itself. So therefore, they will not form gel when they are still hot. Means they can only form gel when it undergo when it undergo cooling. Okay, so after heating, it cools down, then gel will form. So that is translucent gel. Okay. Good thing about this translucent gel is they are less prone to syneresis, means they are more stable type of gel. Okay, so this is the native state of the protein. Okay, so when you apply heat, and of course in the presence of water, it will form it becomes unfolded. Okay, becomes unfolded. Okay, due to the denaturation. Okay, unfolded means remember when I explained on the structure: primary, secondary, tertiary, quaternary. Unfolded means let's say the structure is quaternary, it becomes tertiary and secondary. Okay, and if the original structure is tertiary, it becomes secondary and primary, so it becomes unfolded. Okay, so this is the unfolded state of the protein. Okay, for the translucent, it can only form gel upon cooling. Okay, and for the opaque or coagulant gel, provided it has large amount of non-polar amino acid, it will form it will aggregate and then form gel, even though it's still hot. Okay, not necessarily cools down like translucent gel. Okay, so this part here will determine whether the gel form is either coagulant or translucent. So means based on the amino acid, whether high amount of nonpolar residue or low, okay, low amount of nonpolar residue. Next, we move on to protein quality. So what is protein quality? Okay, so it's very much related to essential amino acid. So if the essential amino acid, remember it's the amino acid that is needed from food. Okay, your body needs it from food. So if the food contain high essential amino acid, then we can classify that as first class protein or high quality protein. So example of high quality protein includes meat, okay, dairy products, eggs, and then a few legumes such as pea and soya bean. So normally animal protein will have more essential amino acid compared to plant proteins. The intermediate quality protein are the one derived from plant material like potato, rice, wheat, and the poor quality protein normally from cassava and other roots and tubers. Okay, for example like potato, okay, from roots. Okay, the next part is chemical alteration of amino acid. Now protein, when they are processed to give you the end product, okay, of food, normally it involve high temperature processing. Okay, this high temperature processing will change the protein. Okay, for example of chemical changes that protein undergo are racemization, hydrolysis, desulfuration, and also deamidation. And this reaction can modify the amino acid in the protein. And this modification normally is undesirable. First of all, we look at racemization. Okay, this normally occur in food containing protein that undergo alkali treatment processing, and of course thermal, okay, high temperature. So when your food containing protein is at alkaline condition and at high temperature, it can leads to racemization reaction. What is racemization? It's actually converting the L amino acid into D amino acid. Okay. So the residue of amino acid like aspartic acid, serine, cysteine, okay, glutamic acid, phenylalanine, asparagine, threonine. These kind of amino acids are racemized faster than other amino acids, and then it is 10 times faster in protein than in the free amino acid itself. Okay, so if your protein is composed of all these joined by peptide bond, it will racemize 10 times faster compared to individual amino acid itself. So what are the negative effects of racemization. So the biological effect of racemization will reduce protein digestibility and protein quality. Means the protein containing product that intake by your body will be reduced in terms of its digestibility, and of course the quality of the protein also will be reduced. So instead you get good high quality protein containing product, it will be less because it's because you already undergo racemization. So why is it what causes this reduce in terms of digestibility and protein quality is due to the peptide bond. Remember, the amino acids are linked by peptide bond to give you protein. Okay, so the peptide bond, okay, of these D amino acids are less efficiently hydrolyzed, so it's not properly broken. Okay, so that's why it leads to the decrease in terms of digestibility and quality. The next one is less efficient of the amino acid being absorbed through the intestinal mucosa cells of your body due to this less efficiently hydrolyzed peptide bond. And even if it is absorbed, okay, it cannot be utilized or used in vivo protein synthesis of the body, okay, due to the amino acids after hydrolysis is not the right how you say, the right molecule. Some of the D amino acids, for example, D-proline, has been found to be neurotoxic in chicken, okay, due to this less efficiently hydrolyzed amino acids. So go back to the processes of racemization. So racemization will occur if the protein containing product are heated, means it undergo processes like baking, grilling, broiling, okay, at more than 200 degrees Celsius, okay, which leads to the decomposition of the pyrolysis of the amino acid. And several pyrolysis products from this broil or grill meat are highly mutagenic. Okay. Example of this highly mutagenic or carcinogenic product from pyrolysis, the residue of tryptophan and glutamic acid amino acid residues. Okay, and these compounds produced at this high temperature of 190 to 200 degrees Celsius are categorized or are known as IQ, imidazoquinoline compound. And these compounds are the condensation product of sugar and certain amino acids like glycine, threonine, alanine, and lysine. So these are the three compounds from racemization process, specifically broiled fish. Okay, compound 1, compound 2, compound 3. Okay, IQ compounds. Okay, this is the mechanism of racemization reaction. First of all is the abstraction of alpha proton from the amino acid residue, okay, to give a negatively charged carbanion. Okay, of course the condition has to be at alkaline. Okay, and then the temperature is high. Okay, about 200 degrees Celsius. Now this carbanion is optically inactive intermediate. So therefore, proton, okay, is added back. Okay, is added back to form either D or L enantiomer. Okay. Besides that, this carbanion can also undergo beta elimination, okay, to form dihydroalanine, okay, DHA, okay, and this DHA, dihydroalanine, can further react with other residue amino acid, okay, to form cross-linking reaction. Now, the cross-linking reaction, okay, proceeded after the formation of dihydroalanine, okay, especially when the food undergo processes high processing temperature and at alkaline pH, which is the racemization reaction just now. Okay, this racemization further will induce a cross-link formation. Okay, and that dihydroalanine, okay, can react with lysine residue, okay, lysine residue to form lysinoalanine. And this lysinoalanine is the major cross-link found in alkali treated protein. And what are the biological effect of this protein cross-link of alkali treated protein is reduction in protein digestibility, which is also equivalent to racemization just now. Okay, racemization also leads to reduction in terms of protein digestibility. So does protein cross-link. Okay, example of this is inability of trypsin to cleave the lysinoalanine covalent bond, and most of it will be excreted in the urine. Okay, cannot be absorbed in the body. Okay, so this is the mechanism of protein cross-linking, okay, from DHA to lysinoalanine. Okay, other example is lanthionine. So this table shows the content of lysinoalanine in processed food. Note that the lysinoalanine will be very much high, especially when the food is in alkaline condition and treated at high temperature. Okay. So, if racemization and protein cross-linking leads to negative effect, Therefore, chemical modification is needed, okay, to avoid the negative effect. Okay, two of them are alkylation and acylation. Okay, so these two reactions will alter chemical properties of protein. Okay, but then it won't give the negative effects such as reduce in digestibility or reduce in absorption. Okay, and this chemical modification will improve the functional properties of protein. For example, alkylation, it retards malabsorption. Acylation improve protein solubility. Therefore, if protein solubility is improved, the digestion will also improve. Several side chain of proteins are reactive, and example of the side chain that are reactive are lysyl group. Lysyl residue. This lysyl residue is the amino acid radical residue of lysine amino acid. And these lysyl residue are one of the reactive side chain. Another one is SH group of cysteine amino acid. So there's only two amino acid with sulfur, which is cysteine or methionine, and cysteine are the most reactive nucleophilic groups in protein. So these two are suitable for modification of food protein. Okay, for example, alkylation here. So this SH, an amino group, can be alkylated, okay, by reacting with iodoacetate or iodoacetamide at alkaline condition. Okay, reaction with iodoacetate will eliminate the positive charge of the lysyl residue. Okay, the lysyl residue, and it will introduce negative charge at both of these lysyl and also cysteine residue. Reaction with iodoacetamide will also increase in electronegativity like iodoacetate, and this reaction with iodoacetamide will block this sulfahydryl group. So when it's blocked with this, okay, introduction of this group here from the iodoacetamide, it will prevent polymerization of disulfide bond. Okay, so the reaction with iodoacetamide, okay, will block the sulfahydryl group, so the sulfide-induced protein polymerization cannot occur. Besides using iodoacetamide, sulfahydryl group can also be blocked by reaction with N-ethylmalamide. Okay, so block, then further polymerization of sulfahydryl group cannot occur. So amino groups of protein, on the other hand, can be alkylated with aldehyde and ketone, or reducing sugar in the presence of sodium borohydrate as the reducing agent, or sodium cyanoborohydrate as alternative. So if aldehyde and ketone is used as the reducing agent, it will lead to formation of hydrophobic protein. Okay, and if a reducing sugar is used instead, it will lead to the formation of hydrophilic protein. So reaction using aldehyde and ketone and or sugar will result in the formation of glycoprotein as the end product, and this glycoprotein has superior forming and emulsifying properties. Next is acylation chemical modification. Um, in acylation, the amino groups of the protein are acylated by reacting with several acid anhydrides, and the most common acylating agent used are either acetic anhydride or succinic anhydride. And these acylated protein are more soluble than the native protein itself. For example, to increase solubility of casein or less soluble protein, we can acylate this casein or less soluble protein by acylation using acid anhydride. So this is the mechanism of acylation. So either using acetic anhydride or succinic anhydride. So the reaction of protein with acid anhydride will leads to the elimination of the positive charge of the lysyl residue, okay, and leads to increase in electronegativity. So replacement of the positively charged lysyl residue with negative change of the lysyl residue, okay, leads to increase in electronegativity, and further increase in electronegativity, and this increase in electronegativity will lead to the unfolding of the protein, or means denaturation, okay, from tertiary to secondary or from quaternary to tertiary. And that concludes the second part of protein.